Okay, so hello everyone. In this video, I wanted to make a brief introduction into what is an AC motor and also explain the different types of AC motors that we have available. Okay, so in general, we can say that AC motors can be classified into two major groups. We have single phase and polyphase motors. Okay, and the difference between single phase and polyphase motors refers to the fact that we are the number of sinusoidal voltages that we need in order to power these type of devices. Okay. And also we can classify AC motors into induction, also called asynchronous motors, and synchronous motors. Okay. And well, these induction and synchronous motors can be further classified into single phase and polyphase. Typically, we use single phase AC motors for low power applications, and polyphase motors are used for high power applications. And in general, we can say that induction motors tend to be cheaper compared to synchronous motors. Okay. And well, here in this figure, I am showing you what is the general structure of a single phase induction motor. In particular, I am saying here that this is a squirrel cage induction motor. And you can see here at the right side that you have two main parts similar to DC motors. We have the stator, okay, in which we have windings, okay? And also we refer to the windings in the stator as poles, okay? Here we have another pole and here, well, we are connecting here to these windings at the stator, the sinusoidal voltage, okay? This is connected to these terminals. And in the rotor, okay, we have a conductor, okay? A conductor that has the form of of a squirrel cage, no? That's why we call it a squirrel cage induction motor, because in the rotor we use a conductor that is arranged in a way that it's very similar to a squirrel cage, okay? But the reason of using this squirrel cage structure is to ensure that we can induce a voltage in the rotor, okay? The main idea is that we want to induce a voltage, okay, in the rotor, okay? And remember that we can induce this voltage, okay, to the rotor because we know that we can produce varied magnetic field in the stator. In fact, the reason of using a sinusoidal waveform connected to the windings of the stator is that we can produce a rotative magnetic field in the stator that can induce a voltage in the rotor. An induction of a voltage in the rotor allows us to produce a torque in the machine that allows the motor to spin its rotor. Okay, so that is like the main consideration. No, we want to well, this is the main consideration of an induction motor that basically we are producing a rotative magnetic field in the stator with the purpose of inducing a voltage in the rotor that consequently allow us to produce a torque. No, that helps the machine to start turning or spinning. This is another point of view of a single-phase induction motor. Typically, in the rotor, we have a conductor in the form of a squirrel cage. And also, we have windings in the stator, okay? And these windings, connected to a single-phase AC voltage, allow us to produce a rotative magnetic field that has two main purposes: to induce a voltage in the rotor, but also produce the rotative magnetic field that we need in order to produce a torque in the machine. Okay, so this is like another schematic in order to illustrate how single-phase induction motors are configured. Now, in the case of a three-phase induction motor, the reason of using three phases is that we want to produce a continuous rotative magnetic field that produces higher torque. Okay, so the way in which we can generate a three-phase induction motor is by connecting three sinusoidal waveforms to each of the windings of the motor. For example, here in we have a phase number A, in which we have two windings, okay, this one, and these two windings are connected to this sinusoidal waveform, okay? So the idea of using a three-phase power supply is that we can use this arrangement in order to generate a continuous a rotative magnetic field. But compared to the single phase motor, in this case, using a three-phase voltage supply can help us to produce a higher torque in the machine. Okay? So that is the main reason of using three-phase induction motors, that we can produce a higher torque, and also that is translated to more power that we can transmit by using this type of electric motor. Now, uh, we can also have, well, as I mentioned before, we have induction and synchronous motors. But the difference between, or the general difference between induction and synchronous motors is that in the case of the induction motor, that is this one, the speed, okay, of the stator, of the rotative magnetic field produced in the stator is greater compared to the speed of the rotor, okay? But in the case of the synchronous motor, we have a similar arrangement. No? We have a stator, no, in which we are producing a rotative magnetic field, but in the rotor we have a conductor. But in order to produce a voltage in this rotor that can help us to produce consequently magnetic field, what we do need to do is to connect this conductor in the rotor through with a DC supply. Okay, we can use this DC supply. No, we can connect here a battery, and this battery will power this winding. And by doing that, we can produce a current that consequently produces a magnetic field that interacts with the magnetic field in the stator. Okay, but in the case of the induction motor, we need to induce the voltage in the rotor. Okay, but in practical terms, this configuration, contrary to an induction motor, can help us to have the same stator speed and the same rotor speed. That's why we call them synchronous motors, because the speed of the rotor and the speed of the stator, or more precisely, the speed of the rotative magnetic field in the stator is the same as the speed of the rotor. Okay, but in order to achieve that, we need to use this DC power supply that allow us to produce the magnetic field in the rotor and consequently start moving the rotor of the machine to the produced torque. Okay, so that is like one of the key differences. Okay, the first one is that in the case of the induction motor, we are inducing a voltage in the rotor. And in the case of the synchronous motors, we need to use a different power supply in order to create a voltage in the, well, in order to create the magnetic field in the rotor that interacts with the magnetic field of the stator. And this interaction between magnetic fields produces the required torque. Okay, that can help the machine to start spinning. Okay, also we can have permanent magnet synchronous motors. Okay, so the main difference compared to the DC excited synchronous motor is that we can instead use magnets in the rotor. Okay, here we are placing magnets that automatically will generate their own magnetic field. And that is the main difference with the induction motor. No? In the induction motor, we need to induce a voltage in the rotor in order to produce a magnetic field that interacts with the magnetic field of the stator. Okay, but that is the main difference. Also, the use of a permanent magnet in the rotor help us to have a synchronous speed between the speed of the rotative magnetic field and the speed of the rotor. Okay, so that is another factor to consider. In fact, the permanent magnets synchronous motors tend to be also more efficient compared to induction motors. No, they have a higher efficiency compared to the induction motor, and also the use of a permanent magnet synchronous motor also translates with a higher price. Okay, because in this case we need to use permanent magnets in the rotor. That, well, it's very difficult to extract these magnets from the earth, so that's why they have higher costs. Okay, so there is like the main difference between permanent magnet synchronous motors and induction motor. Okay, and well, if we can make a comparison between induction and synchronous motors, we can summarize them in the following points. The first one is that the rotor speed In the case of the induction motor, is always less than the stator rotating field. In the case of the synchronous motor, as we stated previously, the, the rotor speed is the same as the stator's rotative field. Also the rotor type, in this case, in the induction motor, we are using typically a squirrel cage rotor, but in the case of the synchronous motors, we need to use a DC-excited rotor or a permanent magnet, no? Also, when in the induction motor, you don't need external excitation, no? You are basically inducing the voltage in the rotor in order to start spinning the machine. But in the case of the synchronous motors, well, you need a DC external supply or permanent magnets. Okay. Also, the induction motor is self-starting, and in the case of the synchronous motors, well, they are not self-starting, so you need to place this DC voltage in the rotor in order to allow the machine to start spinning. Also, well, in the induction motor, we have a factor that is called the slip. The slip, I will talk about this in the following slides, but basically the slip is the difference, no? It's basically a percentage that relates the stator rotative magnetic field speed with the rotor speed, and we divide this by the stator speed and multiply this by 100, okay? So basically this slip tells us about the difference between the speed of the stator rotative field and the speed of the rotor. Okay, for the case of the induction motor, well, the slip is always different from zero. But for the case of the synchronous motor, since we don't have a difference in the speed between the stator and the rotor, well, this slip is always zero. Okay, because the difference between the rotor magnetic speed and the stator rotative magnetic field are the same, okay, because they are synchronized. Also, well, the efficiency in the induction motor, the efficiency is very low. It has a very high power factor. In the case of the synchronous motor, the efficiency and the power factor are typically higher. Especially, we can use these synchronous motors for higher for power factor correction. Common applications, typically induction motors are used for industrial drives, fans, and pumps, and synchronous motors are commonly used for constant speed drives and power factor correction. Okay. So also we have, well, as I mentioned before, either using an induction or synchronous motor, we need to power these devices. And in order to power these devices, we need to use a three-phase voltage power supply. Okay, this is basically the voltage, but we need three sinusoidal waveforms, okay, in order to power this type of electric motor. But there is an important factor here. The difference in phase between the voltage 1, the voltage 2, and the voltage 3 needs to be on 120 degrees. The reason of that is that, as I mentioned before, we are using three-phase AC motors because they can provide the higher power, no, or the higher torque. But in order to ensure that we can generate a rotative magnetic field that is continuous and also produce a constant torque, we need to well, generate a three-phase power supply that has three waveforms that are out of phase of 120 degrees. Okay, but these separations allow us to generate this rotative magnetic field with higher torque. Okay, compared to only using the single phase motor. Okay, so we need the following form of the voltage waveforms in order to ensure the rotation of the magnetic field produced in the stator. Okay, and also we can connect AC motors in different configurations. For example, you can use a star connection or a delta connection. The main difference between one and another one is how the voltage, what is the voltage and the current that is consumed by each of the phases of the motor. So here, this delta and star connection are basically used for three-phase induction motors. And for example, if you analyze the voltage that is used to power an AC motor in a star connection, you can observe here, if you analyze this loop, that the voltage is divided between the voltage of phase number one, that is this one, and the phase on phase number two. Okay, so This means that the line voltage, okay, is greater compared to the phase voltage. But also you can observe that the line current, no, this is the line current or the of the current provided by the power supply, is also well, in this case, the line current is equal to the phase current. Okay. So this basically, and you can observe that if you analyze, for example, this line current, let me erase this line. This line current is basically the same current that is flowing through the phase number one. Okay, that is in this case is IP1. Okay, so you can observe if you analyze this diagram that the line current is basically equal to the phase current. Okay. Also, you can use the delta connection, and here it has the opposite behavior because the line voltage is basically the same as the phase voltage. Now, if you analyze this loop, okay, you can see that the voltage of the line is equal to the voltage of the phase. Okay, but another thing to consider is that um, the line current, okay, is split between this phase and this phase. So the line current is higher compared to the phase current. Okay, so that is another difference between this connection and this one. Okay, so in the star connection, we say that the line voltage is greater than the phase voltage. Okay, and we say that the line current is equal to the phase current. Okay, so that is the main difference from an electrical point of view of using one type of connection over the other one. And also we can conclude that since the delta connection requires a higher current, no, because the line current is higher, we can say that the delta connection provides a higher torque. Okay. So there are like the main differences between them. And well, these differences are summarized in this diagram. No, that is the only difference is that here we are specifying that for the star connection, the line voltage is equal to the square root of 3 times the phase voltage. And for the delta connection, the line current is equal to the square root of 3 times the phase current. Okay? Okay. So what else we need to explain? Well, this is basically a summary of using a star or delta connection. In the case of the star connection, the wiring configuration is one end of each winding is connected to a neutral. Okay, well, if we go back a little bit, you can see that here we have a neutral connection. No, in this case of the delta, we don't have the neutral. The phase voltage, well, is the same relationship that we described in this slide. The phase current also are described in this slide. The starting current, typically for the star connection is lower and for the delta connection is higher. The starting torque is lower and for the delta connection is higher. The power draw for the star connection is lower and for the delta connection is higher. And the applications, typically the star connection is used for a startup, okay, of the machine, and delta connection is used for normal operation. Okay. Okay. So I think that's all for this first part of the video. I hope you like it and see you later.